Section: Introduction. In this section, we introduce Diffusion Large Language Models, DLLMs, which have recently gained attention in both academia and industry as a new approach to large language models, LLMs. Unlike traditional autoregressive models that generate text one token at a time, DLLMs use a multi-step process to refine a masked sequence into a complete output. This method allows us to consider the entire context, making it suitable for tasks that require comprehensive planning, and it offers flexibility in balancing the number of steps taken and the quality of the output. However, DLLMs face a significant limitation due to their fixed-length denoising process. They start with a fully masked sequence of a set length, which means the final output length is also predetermined. This rigidity can lead to problems. If the length is too short, the model struggles with complex tasks. If it's too long, it incurs high computational costs and can even degrade performance. Additionally, DLLMs lack the ability to adjust their output length dynamically, unlike autoregressive models that can extend their output to refine their responses. We discovered that the model's confidence in predicting certain tokens can guide us in addressing this issue. For instance, when the model is confident about the length being sufficient for a task, it predicts more end-of-sequence tokens. This insight led us to develop DAEDAL, a new denoising strategy that allows for dynamic adaptive length expansion in DLLMs. DAEDAL consists of two phases. First, it starts with a short initial length and gradually expands it based on a metric that evaluates the model's confidence in completing the sequence. Second, during the denoising process, it inserts additional mask tokens where the model's planning is weak, allowing for a more effective output. With DAEDAL, we eliminate the need for manually set, task-specific lengths. Instead, we can begin with a short, standard length and expand it as necessary. Our experiments show that DAEDAL not only optimizes computational resources for various tasks but also matches or even surpasses the performance of fixed-length models that have been finely tuned. This approach enhances both performance and efficiency. In the realm of DLLMs, we note that LLADA has emerged as a significant model, being the first large-scale diffusion model trained from scratch. It has shown competitive performance against leading autoregressive models. Other models, like LLADA 1.5, have further advanced this field by incorporating reinforcement learning for better alignment. While some research has focused on adapting existing autoregressive models into DLLMs, our work emphasizes exploring native DLLMs like LLADA to tackle the challenge of fixed-length inference. Current strategies for DLLM inference have primarily aimed at speeding up generation through computational optimizations. While these methods have improved efficiency, they do not address the fundamental need for dynamic adjustment of generation length based on task requirements. Our work seeks to fill this gap by proposing a novel strategy for dynamic adaptive expansion. Section Summary. In this section, we introduce Diffusion Large Language Models, DLLMs, as a promising alternative to traditional autoregressive models, highlighting their unique denoising process and the challenges posed by fixed output lengths. We propose DAEDAL, a novel strategy that allows DLLMs to dynamically adjust their generation length based on prediction confidence, thereby improving performance and computational efficiency without the need for manual tuning. Section: Overview of Diffusion Large Language Models. In this section, we provide an overview of Diffusion Large Language Models, DLLMs, and their training process. Our goal in training a diffusion language model is to create a model distribution that closely resembles the actual data distribution. We achieve this through a forward and reverse probabilistic process. The forward process introduces noise to the original sequence, progressively masking it until it is completely obscured. At any point in this process, we generate a noised version by replacing each token with a masked token based on a certain probability, while keeping it unchanged with the complementary probability. The learning happens during the reverse process, where we train a transformer model to predict the original sequence from its noised version. We optimize the model by minimizing a loss function that focuses only on the masked tokens, which helps us maximize the evidence lower bound on the data's log likelihood. This pushes our model distribution to better match the true data distribution. During inference, we use a multi-step iterative denoising process to generate text. We start with a sequence filled with masked tokens, and, in each step, the model predicts the tokens for the masked positions, producing an estimate of the complete sequence. We then apply a remasking strategy to decide which tokens to keep and which to remask for further refinement. We find that a low-confidence remasking strategy, where we retain high-confidence predictions and remask low-confidence ones, is effective. This process continues until we generate the final text sequence. However, a challenge arises because the generation length must be set before inference, limiting our ability to adapt to the task's needs. To tackle this issue, we introduce DAEDAL, a two-stage strategy that does not require additional training. This approach allows us to adjust the sequence length based on the task and provide extra space for reasoning when necessary. The first stage, initial length adjustment, focuses on determining if the current token length is sufficient by assessing the model's confidence in generating an end-of-sequence EOS token. We visualize this behavior by comparing EOS confidence for problems that can be answered within the predefined length and those that require more tokens. Our findings show that the model has higher EOS confidence for length-sufficient problems, indicating it recognizes when the length is adequate. Conversely, for length-insufficient problems, the model uses the available space more fully, resulting in lower EOS confidence. Based on this insight, we implement a preliminary length estimation loop before the main denoising process. This loop starts with a short initial length and evaluates the model's predictions. If the confidence in predicting the EOS token is below a certain threshold, we interpret this as a signal that the length is insufficient. In response, we extend the generation length by adding more masked tokens. This loop continues until the EOS confidence exceeds the threshold or we reach a maximum length limit. Through this mechanism, DAEDAL dynamically adjusts the generation length to suit the task before we begin the detailed denoising process. Section Summary. In this section, we describe the training and inference processes of diffusion language models, DLLMs, highlighting how the model learns to reverse a noising process to predict original sequences. We introduce DAEDAL, a two-stage strategy that dynamically adjusts the generation length based on the model's confidence in predicting an end-of-sequence token, allowing for more flexible and task-appropriate text generation. Section: Iterative Mask Insertion. In this section, we describe the second stage of DAEDAL, called iterative mask insertion, which enhances our model's flexibility during the denoising process. We believe that predictions with very low confidence indicate that the model's local context is too limited to express complex ideas. This suggests that the model needs more discursive space to improve its reasoning. Therefore, during each denoising step, we not only identify and fill in high-confidence tokens but also mark the position with the lowest prediction confidence, as long as it is below a certain low threshold. Instead of treating this position as just a difficult token, we label it as an expansion point. When we mark a position for expansion, we replace a single masked token with multiple masked tokens, effectively creating more space in the sequence. This gives the model the necessary room to articulate complex reasoning or detailed descriptions, improving its language and logic in later iterations. Unlike the first stage, which adjusts the overall length, iterative mask insertion is a localized adjustment that happens in real time during generation. This allows DAEDAL to manage complex situations where the needed length exceeds the initial estimate, greatly enhancing the model's expressive capabilities. We also detail our implementation of DAEDAL using LLADA Instruct-8B and LLADA 1.5 to 8B as baseline models. To ensure fairness, we conducted all experiments using the official generation code from LLADA, without any optimizations. Our experiments were run on a server with 8 NVIDIA A800 GPUs, using a batch size of 8. To evaluate DAEDAL's effectiveness, We tested it on 4 benchmarks related to mathematical reasoning and code generation. For mathematical reasoning, we used GSM-8K, which includes grade school math problems, and the more challenging Math 500, which consists of competition-level problems. We measured performance based on accuracy. For code generation, we employed the MBPP benchmark for basic Python tasks and the more complex human eval benchmark for program synthesis, reporting the correctness of generated code in a single attempt. Our results, comparing the performance of LLADA Instruct-8B and LLADA 1.5 to 8B with the fixed-length denoising baseline against DAEDAL, show that baseline performance heavily relies on manually tuning the generation length for each task. We reported baseline performance across 6 fixed-length configurations, ranging from 64 to 2048 tokens. In addition to accuracy, we introduced 3 key metrics: the total number of tokens generated, the number of effective tokens used to answer the question, and the effective token ratio. DAEDAL performed well with a unified initial length, demonstrating superior performance compared to the baselines. Despite starting with a shorter initial length, DAEDAL's 2-stage length adjustment and expansion mechanism allowed it to outperform baselines with the same initial length and achieve results comparable to the best-performing fixed-length configurations. This highlights the effectiveness of DAEDAL and the impracticality of the fixed-length approach, as the optimal length varies across benchmarks, emphasizing the need for dynamic length adaptation. We illustrated this adaptability by contrasting the total generation lengths used by DAEDAL with the fixed length of the best-performing baseline for each benchmark. Unlike the baseline, which is limited to a single length, DAEDAL adjusts its generation length based on the specific problem, resulting in a varied length distribution that reflects task complexity. Our analysis shows that DAEDAL intelligently estimates and generates responses of appropriate lengths, often matching the effective token count of the baseline's best configuration. Moreover, DAEDAL significantly improves computational efficiency. While achieving better accuracy, the total number of tokens generated by DAEDAL is generally lower than that of the baseline at its peak performance. This leads to a higher effective token ratio, enhancing the use of computational resources by reducing unnecessary overhead and minimizing wasted resources on padding tokens. In summary, our findings demonstrate that DAEDAL, through its initial length adjustment and iterative mask insertion, not only matches or exceeds the performance of meticulously tuned fixed-length baselines across various benchmarks but also adapts the length for each task, resulting in significant improvements in both performance and efficiency. Section Summary. In this section, we describe the iterative mask insertion stage of DAEDAL, which enhances generation flexibility by dynamically replacing low-confidence masked tokens with multiple masks to provide the model with more discursive space for complex reasoning. This localized refinement allows DAEDAL to adaptively adjust the generation length in real time, significantly improving both performance and computational efficiency compared to fixed-length baselines. Section: Analysis on DAEDAL. In this section, we analyze DAEDAL, which consists of 2 effective stages that work well together. We performed an ablation study to understand how each core component contributes: initial length adjustment, which is stage 1, and iterative mask insertion, which is stage 2. Our findings show that using either stage alone improves performance compared to the baseline, but combining both stages leads to the best results. This indicates that the stages complement each other and are essential for optimal outcomes. We also found that the initial length is crucial for global planning. When we used stage 2 alone, its performance depended on the initial length. For instance, starting with a very short length, like 64, improved performance compared to the baseline but did not reach the peak performance seen at a longer length. However, starting with a more suitable length, like 256, allowed stage 2 to exceed the baseline's best result. This behavior highlights that stage 2 acts as a local expansion tool, and if the initial length is too short, the overall planning suffers from the beginning. While local expansions can help, they cannot fully compensate for a poor initial plan, emphasizing the need for stage 1 to set a solid foundation. DAEDAL shows strong robustness to the initial length. We verified this through an ablation study on the initial length parameter. Our results indicate that DAEDAL performs consistently well across various initial lengths, from 32 to 512 tokens. On the human eval task, accuracy remained the same across all settings, and variations on GSM-8K were minimal. This suggests that users do not need to fine-tune this parameter extensively. A short, unified initial length, like 64, is adequate for optimal performance. We also examined how DAEDAL's performance is affected by the expansion factor, which determines how many mask tokens are added during each expansion. Our study showed that performance remains stable across different expansion factors, from 8 to 32. This indicates that the specific size of each expansion step is not critical. Whether we use smaller, more frequent expansions or larger, less frequent ones, the model consistently reaches an appropriate total length for the task. This supports our idea that the model has a strong internal estimate of the required length for a given problem. Furthermore, we assessed DAEDAL's sensitivity to the size of the EOS confidence window, which helps determine if the length is sufficient. Our analysis revealed that performance is stable with larger window sizes but declines with very small ones, like 8. Even in this less optimal scenario, we still observed significant improvements over the baseline. We believe the drop in performance with small windows is due to a higher chance of misinterpreting the model's intent. A larger window averages confidence over a broader context, while a small window can lead to premature length termination based on localized fluctuations. Lastly, we conducted a comprehensive study on the 4 key threshold hyperparameters in DAEDAL. We analyzed these in pairs to understand their interdependencies. The high confidence threshold is similar to a decoding strategy that speeds up inference by filling tokens that exceed a certain confidence level. The other pair controls sequence-level length adjustments. Our results showed that DAEDAL is exceptionally robust across various configurations, with many performing comparably to or better than the best baseline. This indicates that DAEDAL can maintain strong performance without needing extensive hyperparameter tuning.